So, good morning everyone. Welcome to Brandforsk and this result webinar with the title Inhibit Fire with Molecules from Nature, Application on Textile. And we have a lot of guests here today. We have Anna-Carin Larsson, Josefien Enman och Biplab from Luleå University of Technology. Welcome. And we also have Edvard Aamodt from RISE in Norway. So welcome. Good morning.
Good morning.
Good morning.
Good morning, all of you.
Good morning.
So this is a really exciting project that you have done, and I'm eager to hear about it in a few minutes. But first of all, I really would like to hear about who are you? Should we start with Anna-Carin?
Yeah, I'm an associate professor in chemistry of interfaces at Luleå University of Technology. I've been the project leader for this project. So I've worked now with flame retardants for a few years.
Yeah, we've seen you here for a number of webinars now talking about on this subject. So welcome. And Josefien?
Josefien Enman, I'm a senior lecturer in biochemical process engineering, and I've been part of this project. So this is my first webinar, Brandforsk.
Yeah, you're very welcome here.
Thank you.
And Rhoda, Afriyie Mensah, should have been here, but she's actually ill today, so we miss her today and hope that she will get well soon. But we're moving on now to Biplab. Welcome, Biplab. Who are you?
I am Biplab. I am working as a postdoctoral researcher here. I am working on this field here last 2 years, almost going to finished. So I am working on fire retardant property of cellulose-based materials, and basically I'm working on cotton and some other textile materials, and also I'm going to study on wood materials. So basically I'm working on mainly cellulose materials. I here in this project I made this chemicals, other things, all the fire retardant samples.
Yeah.
With the guidance of Anna-Carin Larsson. I've done. Thank you.
Yeah, thank you. Thank you. Welcome. And Edvard, welcome. Who are you?
Yes, thank you very much. Yes, my name is Edvard Aamodt. I work at RISE Fire Research at Trondheim in Norway. I've been working there since 2020. I'm a Master of Science, working on testing and research related activities in fire safety. So a little bit of everything. So I was very happy to be invited into this project as well, to do some demonstration tests that we will see some videos of later. So thank you.
Yeah, thank you. So you're all very welcome here. And we'll get more information about your projects in just a few minutes. I'm just going to give the audience some brief information about our work here. So I'll see you in a while during the question and discussion session. Yes, just some short information on Brandforsk. We have a vision, a fire-safe and sustainable society built on knowledge. We work with developing and communicating knowledge to limit the negative consequences of fire in the society. Everything we do is funded by supporting organizations, and last year we raised about 700,000 euro, and so far this year we are up to 640,000, and I hope to get more funding during the year, and you're all very welcome to chip in, of course. We use the money to funding projects, for example this one that you will see in a while. And also with a lot of communication of the results, like webinars, podcasts, and such. We also have a research school for fire safety engineers, and we have scholarships for students. Now, these are the organizations that are supporting us so far this year. It's 61. Most of them are from Sweden, but we also have support from Norway and Switzerland, and that's very, very nice, I think. Now, the program today, after this short introduction, we will get a presentation about the webinar, about half an hour. about the project, sorry. And after that, we will have time for questions. And you can write your questions in the Q&A, or maybe it says frågor och svar, maybe, or whatever language you have on your Zoom. So please write your questions there, and we will answer them after the presentation.
Thank you. I will present the results from our project, Inhibit Fire with Molecules from Nature, application on textiles. So we have a big team. It's me, Anna-Carin, and then it's Josefien, Enman, Rhoda, Afriyie, Mensah, and Biplab, all from Luleå University of Technology. And then we have Ragni, Fjellgaard, Mikalsen, and Edvard Aamodt from RISE in Norway. So the aim of the project was to develop new environmentally friendly and safe fire flame retardants, FR, we will call them for short, by using compounds which are naturally occurring and harmless to humans and the environment. So the background is that there is a large fire load from combustible materials in a room, and many flame retardants used today are bad for both health and environment. So there is a need to find better options. So then the question is, can we use safe molecules from nature? Those molecules could then be extracted from waste materials or produced by microorganisms. So we will look for chemicals in nature that has favorable structures so that we think that they could work as flame retardants. So the idea is then that those molecules will take heat when they decompose. The fragments that form can terminate the chain reaction that is a fire. Phosphate groups are known to cause charring, which prevents the emission of pyrolysis gases. Species containing nitrogen are known to cause gas formation, which can dilute and quench the pyrolysis. And molecules which have ring structures can form a char that can insulate the underlying material. So we know from before that fyric acid has good fire retardant properties. It's a molecule that can be found in nuts and grains. Plants use it to store phosphorus, which they need as an energy source. In nature, we also have a group of chemicals called purines. Fyric acid is an acid, and those purines are bases, so we will call them PB for short when we discuss them in general. They all have very similar structures, nitrogen-containing rings, and then there are small differences. Theophylline is one molecule that is found in coffee, chocolate, tea. Adenine and guanine are found in our molecules. DNA and RNA are built partly from those molecules. And uric acid is the metabolic product. When those metabolize in the body, they transform to uric acid. So we started by doing screening tests. We chose 3 different materials, cotton, polyester, and wool. We used pure fyric acid and pure purine bases, made aqueous solutions, dipped our textiles in those solutions with varying molar ratios between fyric acid and the purine, and also different concentrations of the PA. So with this first screening, we will then look at which specific compositions give the best properties, and then we continue with more detailed tests on those. And in the end, we make a fire demonstration test to see if the small scale results will also work when we have a bit bigger scale. So from the screening tests, we could see that some samples could be discarded immediately because of their material properties, like theophylline on wool didn't bind very well. So instead we got those precipitates. So that is, of course, not a good result. So we cannot continue with this. Some materials and combinations with those flame retardants made the material very stiff. And in some cases, we couldn't dissolve the purines in our solution because the pH and molar ratios didn't fulfill the criteria. So from those mixtures then that gave good material properties, we continued with simple burning tests. So we just ignited the samples with a small flame. So untreated cotton in 8 seconds, it has completely burnt. And this one of our combinations, adenine and fyric acid, 10 seconds in contact with the flame, and we only have some charring. So we could then measure how much mass loss we got from the different tests. This was a quite okay method for cotton, but for polyester, it's known that polyester shrinks, so then it withdraws from the flame. So it was a bit difficult to trust those results from the burning tests. But we can see, at least for cotton, some results here. Pure cotton lost almost the full weight. And then we can see that the molar ratio matters from this figure. When we have different molar ratios between PA and, in this case, theophylline, it's more or less charring. We can also see that it matters which purine we have. TP, PA, and PA and adenine. So adenine is a bit better than TP. Guanine and uric acid didn't perform very well. And we can also see that the concentration matters. 3%, 5%, 10%. More of the mass is remaining after those burning tests. We also screened with the microscale combustion calorimeter. We can see also here that all flame retardant mixtures that we tested have improved fire properties. Peak heat release rate is significantly reduced, as well as the heat release capacity. And the results correlate with the burning test, so we can see that 10% and TP and adenine is better than guanine and uric acid. For polyester, we can see similar results for all of the mixtures. All of them significantly reduce the heat release rate, and especially the 1:4 molar ratio gave good results. Even if wool didn't mix well with the PA, we still wanted to do one test with wool just to see what it looks like. And we can see that also on wool, the fyric acid reduces the heat release rate. So from those screening tests, we selected 3 samples to continue with. So they are all 10% solutions of PA. And then we chose cotton with TP and adenine, both molar ratio 5:1, and polyester adenine 4:1. So here we can see from the microscale combustion calorimeter, C, untreated cotton, and P, untreated polyester. So heat release capacity decreased, peak heat release rate decreased, total heat release rate decreased. The temperature is at the lower temperature that this heat release takes place, especially for cotton, very low temperature compared to untreated, and also for polyester. The degrading here starts a bit earlier. And the mass loss is also reduced. We did cone calorimeter tests. For cotton, we used 25 kilowatts per square meter, and for polyester, 35. Untreated cotton burned completely, so there is no photo to show of that one. Both TP and adenine, we can see that they form a char layer here, which stops the fire, so it self-extinguishes. Untreated polyester and polyester with adenine PA, both of them melt and it's not very big difference on those photos of the mass that is remaining. But if we look at the collected data, we can see also here that the samples ignite earlier, but they also flame out earlier. So the burning time is shorter for the treated samples because they self-extinguish them. So less heat is released. And the peak heat release rate is also lower. Some smoke production on the cotton, but reduced in polyester. And the FIGRA index is shown here as well. Thermal gravimetric analysis can be done so we can see at which temperatures we lose mass. So this is in air atmosphere. So here we first lose some mass from water evaporating. Here the flame retardants start to break down. And here this breakdown, as we'll see later, causes charring that prevents further breakdown. So it's a very slow decrease in mass here. While the treated samples, they degrade almost completely, and then some small residue is slowly combusting until all mass is lost. This is the derivative of the curves. In argon atmosphere, we don't get any ignition because we don't have any oxygen here. So then we can also see first some water disappearing, then the thermal degrading of the flame retarded samples, and then the mass is remaining, almost half of the mass, while the untreated samples degrade completely. With differential scanning calorimetry, we can investigate heat changes during those processes. So endothermic reactions take heat from the fire. So we can see here evaporating water is an endothermic process. And here number 2 is when the flame retardant breaks down, and then we can start the charring. So here peak 3 is the charring mechanism. So when the surface has charred, there is nothing more happening, a small degrading of the sample. The untreated sample, then it degrades completely. And that is then endothermic when we break down the molecules that make up the cellulose fibers. And the same for polyester. Polyester doesn't absorb water, but the flame retarded sample has some water that is released. Here the melting point of polyester, and here the polyester starts to degrade. Also here we can see some small exothermic peaks from some char formation. We can also use magic angle spinning NMR to look at the atoms in the sample. So this is carbon atoms that we are looking at. So we took our samples and put them in an oven at 350 degrees. And then we looked at the samples, what has happened. So we can see that untreated cotton, we still have the cellulose structure intact. It hasn't started to degrade yet. But the samples with flame retardant on, they have completely charred. So we see that there is no signals from the cellulose itself left. We only have peaks here that says that we have some aromatic carbons on the surface. And with the phosphorus atoms in the phytic acid, we can see what happens with the PA molecules. So at room temperature, we have the signal here from the PA. Then when we heat it, the phosphate groups start to change. So we see that we get new peaks here to the right of the original peak. And for adenine, we have a bigger peak further right than with TP. So those peaks to the right, they tell us that the phosphate groups have polymerized. and adenine forms a bit larger polymers at this temperature, 350. And polymer formation is endothermic, and it also forms a barrier on the surface. We also used scanning electron microscopy with X-ray analysis here. So we can see that the fibers are not damaged from the flame retardant. Untreated and treated cotton have similar fiber structure. And we can also see that we have both nitrogen and phosphorus on the surface. So both the fyric acid and the purine base has absorbed on the cotton fibers. So based on those more detailed tests, we decided that adenine and fyric acid gave the best results. So then we prepared cotton and polyester with this mixture and sent to Norway for a mock-up furniture test with upholstery filling based on standard. So we started with a small flame ignition source, and we could see that untreated cotton and polyester ignites after 15 seconds and burn the whole experimental time. So this is untreated cotton, and here is untreated polyester. So we can see that cotton burns a bit slower, and we get much more damage on the polyester. So we have videos of all those experiments, so you can go and look at this YouTube link. But I'll try to show you some results here, see if it works. Untreated cotton and cotton with adenine and PA. So the timing differs a few seconds, but you will still see a difference. See that the untreated cotton here to the left starting to burn and the fire is spreading, while the treated cotton still only have a small black spot. We can jump forward here, so nothing happens. So the second repetition of the experiment. A small black spot again, but then nothing more happens. So the cotton passed the first test here with the small flame. So then a new test was made with the crib. Here. So it's crib 5. So after 2 minutes, 15 seconds, the fire was extinguished and the experiment stopped for this untreated material. So crib 5, then the fire is supposed to continue for 10 minutes before the experiment is stopped. So we can jump ahead a bit here. So after 4 minutes here, the crib itself has burnt completely. And we can see that there is some charring on the cotton. And it expands very, very slowly. So then after 10 minutes, the experiment stopped. So this first experiment, then the material passed also the crib 5 test. It didn't continue to burn here during those 10 minutes. So we can summarize those results and see that for polyester, the treated sample burnt less intense than the untreated, and the same for cotton. Untreated burnt more intensely than the treated one, which didn't burn at all, it just self-extinguished. Polyester here with the flame retardant, in one test it passed the small flame test, and in the other it didn't. Cotton passed those small flame tests, but the crib only in one of the tests. So this is the second one where it didn't pass the crib 5. So we can draw some conclusions from this study that fyric acid and adenine on cotton, 5:1 molar ratio, show the best flame retardant properties, and theophylline in the same molar ratio was close behind. Cone calorimeter measurements show that the samples ignite earlier than untreated, but they also flame out. So burning time is halved for both cotton and polyester. And also the heat release is reduced compared to untreated samples. The char formation caused the samples to self-extinguish after only a small mass loss, and it's the phosphate groups in PA that is known to cause this charring. TDA and DSC correlate well with each other, so we can describe the thermal degradation process in 3 steps: evaporation of water, degrading of the FR molecules, and char formation. And then the char hinders the samples from degrade further. And the NMR measurements also support the interpretation of TDA and DSC data. So we see that the flame retardant cotton has degraded completely into char before the ignition temperature of cotton is reached, which then protects the fire from spreading in this material. And the degradation of the fyric acid has transformed the phosphate part into a polymerized material. SEM images show that the structural integrity of the textile fibers is conserved after treatment. And NMR data also didn't indicate any structural differences in the cotton. And we have both fyric acid and purine base on the fibers. The fire demonstration tests on a mock-up furniture show that the flame retardant treatment with adenine and PA had fire ignition inhibiting effect, especially for cotton. We could also see that if we use only PA, we also have a relatively good fire performance, but the textile fibers become hard and stiff. So the addition of this purine base improves the quality of the material itself. So some recommendations then. The fire demonstration tests in the project showed that those flame retardant formulations that we developed have the potential for practical application in furniture upholstery, which can be beneficial then for both suppliers and end users, and especially persons with risk factors benefit from a fire-safe living environment. So some future work that could be done is to increase the scale and do a full-scale test on a real-size furniture and also other interior details to get the proper evaluation. We haven't investigated the durability of the flame retardant with time and if it's resistant to leaching and wear. So these are also important parameters for a flame retardant. And to continue, we can also look for waste sources where we have a huge amount of those components, so we can extract them from the waste, and then which methodology to use for this extraction, because you can extract the material from waste sources with different methods. Another option is also to find microorganisms and bioprocesses so we can produce those components of the flame retardant. So finally, big thank you first to Brandforsk for the financial support for this study, and the members of the reference group have given valuable input on all our meetings and on the report. So Leif, Mattias, Mikael, Anniken, Robert, Lynn, Anne, Mohammed. And Tobias Sparman and the Swedish NMR Center for assistance and resources for the NMR measurements, and Yang Yu at LTU for assistance with the SEM measurements. So thank you.
Thank you very much, Anna-Carin. Welcome back, all you researchers. And we will go to the question and discussion session. And good morning, Ragni. Good to see you. The other researchers, they presented themselves when we started up this webinar this morning, and I would love to hear about you. Who are you, Ragni?
I'm a research scientist at RISE by Research, so I've been my colleague with Edvard, who is leading the project from our side.
Yes, welcome. And to the audience, please write your questions in the Q&A or frågor och svar or whatever it says on your Zoom. And I can also inform that the report and all the movies from the testing, you can also find those on the Brandforsk webpage. Well, let's jump into the questions because we already have some. The first one is, have you considered looking at smoldering tests? With fabrics, a classic scenario is a cigarette test and is a common test for furniture to show reduced risk for ignition. Have you considered that?
I can answer that, I guess. So I discussed it a little bit with Ragni, and having a smoldering test with cigarettes can be quite interesting. I don't have that much experience with it, but it could give us some additional information, and we see it as a little bit milder test, and so we wanted maybe to choose a little bit more a worse scenario, and so that's why we went for the small flame test with the flame exposure test. So, and also to say that we had to limit our number of testing as well due to budget constraints. So it would be nice to do some additional tests with different conditions, definitely.
Yeah. Thank you. And we have a lot of questions about toxicity. Both, I think, during that smoldering part, for example, you had some smoke. Is that smoke? How toxic is that? Have you looked at that so far, or is that yet to come?
That would be very interesting. I think we haven't looked at that, but that it could definitely be something F-tier test setup as well. Yeah, maybe something for further work, probably.
Yeah. Josefien?
Well, we haven't tested the toxicity, but I wouldn't say that it's that toxic compared to would it
it would be if it was a real fire. So
No. But I mean, if I fall asleep on the couch tonight, losing my cigarettes, even though I'm not smoking, and it will start smoldering really near my face. How toxic would it be? More or less toxic, do you think, if you have treated the fabric?
more or less toxic. Yeah, I cannot really answer that. Sorry. But
Next project.
yeah,
Well, I
it has
guess,
to be investigated.
Yeah, but there is no safe smoke anyways. So if you have a smoldering fire quite near your face when you're sleeping, it's not ideal. So I wouldn't necessarily expect the quite small amounts of new chemicals added here to significantly contribute. But the burning of your bed and your mattress and these things might be more harmful, I guess.
And we see that it self-extinguishes quite efficiently also with the higher power of the flame source compared to what the cigarette can give.
Yeah. Well, yeah, good. Another angle on toxicity. How do you know that these FRs that you have now worked with are non-toxic and safe and environmentally friendly and such?
I mean, these are molecules that we have them in our bodies and we can consume them. So in that sense, they are very untoxic.
Yeah. Very good. I was thinking when I was looking through your presentation, and I was amazed that you had a reaction actually in the temperature raise. The reaction came earlier, and first I thought, oh, that must be bad, but then you say that's good because you kind of destroy the fabric before it actually can get dangerous. Can you explain that a little bit more?
Yeah, that when I started with those flame retardant research, that was my reaction as well. But that doesn't look good that we destroy the fabric so early. But if the fabric reaches 350 approximately, then it degrades completely and we get a lot of pyrolysis gases that ignite and we get a fire. But when we start to degrade the material already at 250, first we get the charring, so we prevent the rest of the material from degrading and igniting. And we also stops the temperature from rising further if we don't get any ignition earlier.
Right, because it's endothermic.
Yes.
In that phase, yeah.
The first degrading is endothermic, so we kind of chars the surface, prevents the total degrading. And this happens at the lower temperature, so we don't reach the temperature at which it ignites. So then it's self-extinguished.
Right, fascinating. So you really don't. If I want to protect the fabric itself, this may not be a good way because the fabric is destroyed, but I protect myself, but not the fabric. Is that correct?
Yeah, you form the char, which then stops the fire from taking up the speed. So we saw that it self-extinguishes and we only get this charred layer. And it's much less heat release compared to if it really starts to burn. So you will be more protected.
Yeah. Fascinating, I think. You were talking about future works and such, and what do you think? What is the next step for getting closer to a product on the market? And I mean that's a quite a long path to walk, I guess. But what does that look like?
Yeah, we can do more tests, go into even bigger scale to see that it really works on real furniture. And we can also play around more, finding a more finer molar ratios that works even better, increase concentrations, and this type of things to improve it. And
fine-tuning,
yeah, and we also then do those toxicity tests of the gases. That's always good point to do. And we also need further studies to look at other material properties than just the flame retardancy. How does it affect the material itself, if it becomes stiff, or if we can wash it, or if we just sit on the sofa, will the flame retardant be removed from the fibers? Those kind of things.
Yeah. If you should do more fire testing, do you think increasing the heat flux, for example, and putting it into harder conditions fire-wise, do you think could you get more information out of the substance that way?
Yeah, we were trying to discuss the 25 if it's fairly low or not. We could do that, of course. It's but setting fire to materials or fabrics is not something I do every day. So you know that we discussed some other. Yeah, Ragni?
Yeah, well, I mean the test methods that you use for these small scale documentation of how a fabric works, it's not necessarily showing us. It's not. It would be nice to look at bigger fires and how they would expose. So not necessarily just with the cone and the varying radiation sources there, but to look at how a full sofa or a full chair would behave. That would be interesting, because it behaves quite differently when you just have a little small flame and when you have a more developed fire. Not sure if I really agree that 25 kilowatts per square meters is that fairly low. If you're in a building and if you sit in a chair and there's a 25 kilowatt fire nearby, then you feel it. You burn your skin, and it's quite intense. But of course, there are more intense fires out there.
Yeah, right. Thank you. So what your do you have any funding for future work with this product, or are you trying to find more funding right now?
We have applied for some funding from Mistra. They will announce in 14th of June, I think, if we pass the first test, and then we'll be allowed to write the full application for competing for the money. And we have also, at the moment, we are recruiting a postdoc who will then work for 2 years with this. So I'm happy if any one of you knows some candidates that can apply, feel free to tell them the information. So that person is then funded for 2 years, and will be able then to do a lot of work, I hope. And then, of course, it's not impossible to send a new application to Brandforsk.
You're welcome to apply, of course. Yeah.
It's been really nice to have this collaboration and look at different, from small scale and molecule level up to the fire testing in Norway. So
yeah, I think it's
it'd be good if we can find a way to continue with that collaboration.
Yeah, sounds good. I mean, this is a problem that many countries have, so I think it should be really possible to have huge collaborations on this. Well, any more thoughts from your side, from the research side on I mean, you're doing a lot of work on this topic in Luleå, and quite amazing to see, I think. So any more news or thoughts from you?
Well, I can mention that this collaboration between Luleå and Frick is also soon a part of a completed PhD thesis that Rosita Amiri is working on these days. So we will announce that on Frick's webpage when it's finished. So she's also looked at these molecules developed by Luleå and adding them to furnishings.
Oh, interesting. That sounds good. Please let us know, and we can spread the news when she publishes. That sounds very good. Get a question about wood. You have been looking into wood earlier, Anna-Carin, but you haven't tested on with this substance, have you?
No.
No.
We focused on textiles since it's an easier material. Since the wood, then you have a lot of problems with differences in humidity, and for us, when we want to get the chemical point of view on a small scale, it's very difficult to get good results if the humidity changes.
Oh, right.
When we add the flame retardant, our first master students that we had, they prepared their samples, dipped it in water, dipped it in the flame retardant solution, and then they wanted to see the mass before and after, and then the mass was lower. But it should be higher when we have flame retardants on it. But then we lose a lot of salts and water from the wood. So we have to control that to be able to get some good ways to interpret our data.
Right.
And of course, textiles is more important to protect, since they burn much more than wood. It's a bit more difficult to set some wood on fire. So if we stop the fire while it's on the textiles, it cannot spread to the wood. So.
No, that's true. The initial fire scenario, we can hopefully save a lot of people if we can get the fabrics less flammable. Well, excellent. I'm a bit curious. I mean, we are right now in a fire safety community, talking to people into fire safety. How do you get a lot of opportunities to present to chemists? Do you go to conferences for chemists, for example, and talk about this, or is it mostly fire safety people that are interested in your work?
So far, we have only presented it to fire people on the webinars, because we need money and time to go to conferences as well. But I think the chemistry audience would also be interested. For now, we present mostly for students, since I teach a lot on different levels. So I present this project to all my students and try to recruit them to come and do thesis projects. We have a chemical engineering student working with flame retardants now.
Good.
And we also present it to high school students as part of recruitment to those programs relevant.
Yeah, good. Very good. Yeah. Okay. Well then, thank you very much for this super interesting project, and I hope to see more of this work. And I also hope that the chemistry people will find your work and take it on further as well. So thank you very much. Hope to see you soon, and to the audience, the report and all the films are on the webpage as well, and the webinar will be on our webpage and on our YouTube channel in about a week. So if anyone missed it, you can advise them to look at that. So thank you very much. I will give some information just to the audience about upcoming works here at Brandforsk.
Thanks.
Thank you.
Bye. Thank you.
So, thank you for watching, all of you, and I just want to remind you about our fundraising. Everyone is welcome to chip in, and you can read more about that on our webpage or just get in touch with me. this was the last webinar for this season. We are now going to our summer holidays, but after the summer we will start up the webinars again. And you can easily follow us on social media or through our newsletter. You will always get all the news about upcoming webinars and other things as well. And this is my advice for your summer. Listen to our podcast. We have a lot of episodes up on your pod player right now, and the last one published today is about forest fires, and they are all in Swedish, but it's a good opportunity to not learn only about fire safety but also to learn Swedish. And I want to thank my colleagues Francis Eurenius and Matthias Hammarin, that is also producing this webinar. Thank you very much. You can see all our earlier webinars on our webpage and on our YouTube channel. So thank you for watching, and hope to see you soon again, and I wish you all a very nice summer. Bye-bye.